Let's jump into it with number one. So number one states the 10-meter beam AB rests upon but is not attached to supports at C and D given F equals 10 kilonewtons. So when reading this question, it's important to note that AB rests on but is not attached to the supports C and D. So what that is telling us is that the bar is free to slide in the X direction, which means that there are going to be no reaction forces there when we draw our free body diagram. So first, let's go ahead and draw that. So we have our beam going across. I just like to draw it as a straight line. Um, and then we have our force P on the far end, as well as 20 kilonewtons right here, force P. At C, we have C of y pointing up, and at D, we have D of y pointing up as well. Also, right in the middle of the beam, we have force F coming down. So that is what the total free body diagram looks like. Let me draw out these distances, which is 2 meters. Here to here is 3 and 3. And then from here to here we have 2 again. Alright, so that's the entire free body diagram. Always remember to indicate your positive values, like so. And that's the first part of the problem. So we saw the picture that they were giving us, and from the wording of the problem, we were able to determine that at points C and D, there is no reaction force in the X direction, but there is a normal force pointing up in the Y direction. And then the second part of the problem wants us to find the range of P where their beam will remain in equilibrium. So the way that we can approach this is, well, let's take a look. So if we were to set up our forces in the X direction, there are no forces, so we don't have to consider that. But if we set them up in the Y direction, we see that we have too many unknowns. We're trying to solve for P. We have F, we have 20, but we also have 2 unknowns at C and D. So that's 1 equation and 3 unknowns. So that's not going to cut it. So what we can do is we can take the moment about C to eliminate C of y from our equation and get an equation in terms of P and dy. And then we can also, then in the next step, take the moment about D and get a equation in terms of P and C. And then I'll start showing the steps for that, and then I'll explain afterwards what we're doing. So over here, we have the positive counterclockwise direction. We have the moment about C is equal to 0. And let's analyze each of the forces. So from C to P is 2 meters, shown right here, 2 meters. And it's going to rotate C in the counterclockwise direction, so it's going to be positive. So we have P times 2. Then we have our F equals 10 kilonewtons. That's going to rotate it in the clockwise direction, which is going to be negative then, and that is 3 meters away, so we do 10 kilonewtons times 3. Then we have our 20, or our D force pointing upwards, that is 6 meters away, but is rotating in the counterclockwise, so it's going to be positive. So we have plus 6dy, and then our final force minus 20 times 8. And then we set this all equal to 0. Now, simplifying this equation, we see that we have 2 unknowns, but we can solve for P, and we'll get P equals 95 minus 3D. And I did that by just rearranging the equation and solving for P. So now that we see that we have an equation for P in terms of our unknown D, and we want to know when the beam is in equilibrium. So what we can do to figure that out is we know that the p-value that will allow us to stay in equilibrium is when the force of D is equal to 0. So what we can do to find that limit is set this equal to 0 and solve for P. And so for our upper limit of P, we get that it is equal to 95 kilonewtons. And the reason we do that is, let's take an example. Let's say we assume that D is equal to 1. So assume D is equal to 1. Our equation would become P. I'm just using this equation right here. We have P equals 95 minus 3, which is equal to 92. And if we assume D equals 2, we get P equals 95 minus 6, which is equal to 89. So you can see our p-value is decreasing as we increase the force of D. And that's not what we want, because this beam will still be in equilibrium, but we want it when the force of D has 0 contribution. And the way you can think about that is, again, I'll draw the free body diagram, and basically we just have all of the forces except at point D, the force is equal to 0. And you can still set everything equal to 0 because it's not a motion. So that's kind of the reasoning behind it. So now what we can do is we can repeat the process for the moment about D and set it equal to 0. And then we'll get, using the same method as before that we used for taking the moment about C, we get 8 times P plus 10 times 3 minus 20 times 2 minus C of y times 6 equal to 0. We're going to solve for P again. We get that P is equal to 1.25 plus 0.75 C. Again, to find the lower limit, we're going to set this equal to 0. Solve for P, we see that P is equal to 1.25 kilonewtons. And that gives us our range right there. So we have the lower limit right here and the upper limit right here. And we can write that as 1.25 kilonewtons is less than or equal to P is less than or equal to 95 kilonewtons.